Good afternoon, everyone, and welcome to our Faculty Development Program. It is my pleasure to introduce our esteemed guest, Dr. G. Paparao sir, Professor and Head of the Department of Civil Engineering at Gayatri Vidya Parishad College of Engineering, Visakhapatnam. Before embarking on his academic career, he spent 3 years in the industry as a design engineer in Chennai, gaining valuable practical experience that has enriched his teaching and research. He earned his doctoral degree in civil engineering from Andhra University, Visakhapatnam, with a focus on new stirrup detailing schemes for shear demands in reinforced concrete beams and pile caps. His academic excellence is further highlighted by his master's degree in structural engineering from MS University, Baroda, achieved through a prestigious GATE score. His research contributions are impressive, with over 50 research papers published in renowned national and international journals and conferences. His work is prominently featured in esteemed journals such as Indian Concrete Journal, Journal of Structural Engineering, Asian Journal of Civil Engineering, and the Magazine of Concrete Research. In addition to his research, he is also an accomplished speaker, having delivered over 20 invited and guest lectures at various engineering colleges and industries. He has also demonstrated exceptional organization skills by coordinating more than 20 workshops, conferences, training programs, and seminars in his department. His leadership in academia is evident through his successful coordination of two nationwide faculty development programs funded by AICTE and Indian Society for Technical Education. His expertise extends beyond academia into consultancy services, where he has collaborated with several prestigious organizations, including GVMC, Visakhapatnam Port Trust, National Highways Authority of India, East Coast Railways, and various private sectors. His consultancy efforts have generally generated nearly 5 crores in internal revenue for the college, showcasing his dedication to bridging the gap between academia and industry. He has guided over 25 MTech projects and more than 50 BTech projects, and currently supervises 4 PhD students at JNTU, Kakinada, and Andhra University. Dr. Paparao sir is also a life member for the Indian Concrete Institute and the Condition Condition Monitoring Society of India, reflecting his ongoing dedication to professional development and excellence in civil engineering. Please join me in welcoming Dr. G. Paparao sir to share his invaluable insights and expertise. You may start your presentation now, sir.
Okay, madam. Thank you.
Sir,
Yes, madam. Yes, madam. Yes. It's connecting.
okay, sir.
System. System. Yes.
ఎప్పుడు నేను ఉండను.
Madam, is it visible now? My presentation.
ఒక రోజు
A very
Oh,
good
sir, your
afternoon.
screen is not visible, sir.
Not visible.
Yes, sir, yes. Sir, you do one thing, you share the screen, sir. Once you close that sharing option, again you share it. It will come.
Yes, sir. Yes. Now, sir.
Yes, sir, fine. Title slide is there. We can proceed, sir.
Yes, yes. A very good afternoon, all the participants from academia as well as industry, and also the organizing members. Very good afternoon to one and all. First of all, my sincere thanks to the organizing members for giving me this opportunity to share my experimental observations, which are derived from my MTech students' dissertation works at Department of Civil Engineering, Gayatri Vidyapati College of Engineering, Visakhapatnam. I thank the HOD and the coordinators, and also my friend and my student, Dr. J.D. Chaitanya Kumar, Assistant Professor of Civil Engineering, KL deemed to be University. I feel very proud to associate in this faculty development program on sustainable construction practices, because I am also one of the alumni of the prestigious university, KL deemed to be University. I did my BTech during 92 96 from then KL Konar Lakshmi College of Engineering, Vijayawada. Thank you very much for giving me this opportunity once again. So this is my topic, performance of reinforced concrete beams with sustainable aggregates. My total presentation is divided into three topics. The first topic is stripping time of concretes made with blended and composite cement. And the topic 2 is to investigate the suitability of nano concrete aggregate in reinforced concrete beams. And topic 3 is to investigate the suitability of recycled quartz aggregate in shear critical reinforced concrete beams. So these are all the three topics deals with the sustainable development goals. The coming to topic 1, stripping time for concretes made with blended and composite cement. The stripping time means the formwork removal time. This is the code, one of the code and provision I have taken from IS 456 2000. If you observe, the right side table indicates the stripping time for different concrete elements. For example, vertical formwork to columns, wall beams, okay, between 16 to 24 hours we have to remove the formwork. Similarly for slabs, 3 days, for beams, 7 days, and also for slabs up to 4.5 meters, 7 days, 14. Likewise, these are the stripping time given for different concrete elements. If you see the clause 11.3.1, here it is mentioned the two conditions. One is in normal circumstances where ambient temperature does not fall below 15 degrees centigrade, and also the other one is where ordinary Portland cement is used. These are the two conditions actually given in IS 456. But these, whatever the stripping time given in IS 456 is valid for our ordinary Portland cement. But the code is silent about the blended cements, because nowadays 70% of the cement being consumed from the blended cements like Portland Pozzolana cement, Portland slag cement, and also the new variety of cement has come into the market, which is called ternary cement or the composite cement. So here for and again the code says for other cements and lower temperatures, the stripping time recommended above may be suitably modified. Okay, this is giving for other cements, means other than ordinary Portland cements, and also for lower temperatures, that is below 15 degrees centigrade, these stripping times may be suitably modified. But code is not saying at what duration we need to delay or okay, accelerate. It's silent. So this is one of the topic we have taken okay, for my MTech student. So these are the three cements we have considered. One is Portland Pozzolana cement, which is called which is a fly ash based, and Portland slag cement, which is slag based, and also the new cement is composite cement, which is fly ash and slag based. Okay, composite cement is a ternary cement. It's a combination of OPC and fly ash and slag. Okay, this is the almost 73% being used is our blended cements, and 27% is ordinary Portland cement. All of you are aware about the advantage of blended cement. It reduces the direct and indirect contributions to environmental pollution, and also reduce the carbon footprints. And also for durability point of view, durability of structures also shows substantial improvement by the use of concrete produced with blended cements. So these are the this figure shows the carbon dioxide emissions for different cements. As you can observe, the carbon dioxide emissions for blended cements are less than our ordinary Portland cement, and also the main constituent of cement is clinker. Okay, and also here in our study, what we have done is we have considered 4 types of cements. All these cements procured from the manufacturing unit, which is nearby Visakhapatnam, 100 kilometers away from Visakhapatnam, which is My Home Industries Private Limited, with Maha Cement. They are manufacturing Maha Cement. So this My Home Industries Private Limited has set up their organization in one of the location called Narsipatnam, which is 100 kilometers from Visakhapatnam. We have requested them to provide 4 varieties of cements, because we have not purchased the cements for anywhere in the local distributors, because for better compatibility, we have taken from all these 4 cements from the same manufacturer, directly from the manufacturing unit. So we have procured OPC 53 and also PPC, which is fly ash based Portland pozzolana cement, and Portland slag cement, and composite cement. So these are all procured from the Maha Cements at Narsipatnam. And this is a new cement has come into the market, which is called composite and ternary cement. This is the combination of ordinary Portland cement, slag and fly ash with addition of gypsum. And so this is the material proposed to be used in composite or ternary cement. So in composite cement or ternary cement, the Portland cement clinker or ordinary Portland cement is consists of 35 to 65% of weight, and again fly ash is 15 to 35, and the granulated slag is 25 to 50, plus some percentage of gypsum. But chemical gypsum shall be added, provided that the performance requirements of final product as specified in the standard. So these are the some comparisons between GGBS and fly ash, and here the source is blast furnace steel industry, and the fly ash is thermal power plants. The confirming code is IS 16714 and 3238, and the hydration. This is the hydraulic nature, non-hydraulic in nature. The hydraulic nature means the GG base. It's a pure pozzolanic material. It's a pozzolanic, because if you add water directly to the GG base, it will produce the pozzolanic properties. Okay. So fly ash, it won't directly react with until and unless you add some cement. Okay, that the non-hydraulic, and the permissible replacements are this is because of pozzolanic nature. This is up to 25 to 70%. GG base can be used for industrial applications, and fly ash is up to 15 to 35%. So this slide shows this is the minimum fineness of cement. As you can observe, OPC 225, all three grades, 33, 43, 53. Again, composite cement, if you observe, this is 300 meters. This is very finer cement compared to the other blended and ordinary Portland cement. So here, what our plan is, before using all the 4 cements, just we have assessed whether our cement is okay or not, whether the strengths are they are getting or not. For that, this is the we have tested the cement strength, compressive strength of cement for 3 days, 7 days, 28 days, and we have taken these the strengths from the IS 12269. If you look at this OPC 53, the OPC 53 grade cement should possess minimum 27 MPa at 3 days. Similarly, at 7 days, 37, and 28 days, 53. If you use OPC 53. Similarly, OPC 43, 3 days, 23, 33, and 43. And again, OPC 33, for 3 days, the cement compressive strength must be 16 MPa, at 7 days 22 MPa, 33 MPa. Okay, this is about ordinary Portland cements. If you look at the blended cements, at 3 days, all the blended cements, PPC, PSC, and CC. So all 3 days, the strength must be the same, 16 MPa for 7 days, 22, and the 28 days, 33. Here you can observe almost our blended cements possessing the strength of OPC 33. Okay, almost our blended cement strength equal to 33, our OPC 33 means that 28 days it should get minimum 33 MPa. So likewise, we have tested all the 4 types of cements before proceeding for further investigations. We have cast the cubes with our standard sizes 70 by 70 by 70 mm cube. And here, if you see the IS code as per our minimum compressive strength, at 3 days, it should get our OPC 53 should get 27 MPa, and at 7 days 37, and at 20 days 53. So these are the strengths obtained with our laboratory tests. Okay, so we have got 29 MPa at 3 days. Similarly, 37 MPa at 37.11 at 7 days. Again, 53.06 MPa at 28 days. So therefore, our cement is good. Therefore, we can proceed the further investigations with OPC 53 because it is almost possessing our Indian standard specifications. And similarly, PPC also, this is at 3 days 16 MPa and 22 at 7 days and 33. So these are our laboratory tests. We got 16.3, 22.4 and 33.18. Therefore, we can proceed further with our PPC for further tests. Similarly, PSC, Portland slag cement also we have tested almost up to 56 and 90 days also, okay, because for durability test. So here again, PSC got 16.04, 23.73 and 33. So these the values are meeting our Indian standard specifications. Again, composite cement. This is the ternary cement. Okay, mixture of OPC plus PPC and PSC, or fly ash plus slag plus our clinker. Again, it got 16 MPa at 3 days, 22 MPa at 24.07 MPa at 7 days. Again, 34.4. Again, our OPC also, whatever the cements we have procured from mass cements, or we can proceed further for with these cements. First, we have confirmed our cement strengths before going for further investigation. Of course, this is the same table, and so these are in the other form. OPC 29, 37, 45, again 53. PPC. These are the strengths we have got, and again we have chosen for concrete test. We have chosen M35 grade concrete. These are the mixed proportions we have used for different grades of concrete for different types of cements, OPC and PPC and PSC and CC. So these are the consumption of our different constituents or different cement, water, fine aggregate, and coarse aggregate. So these are the material proportions. And here, this is the our focus is to arrive the stripping time of the blended cements, because IS 456 is speaking about stripping time for OPC. So therefore, we need to arrive with the stripping time for the other blended cements. Okay. So here at 7 days we got OPC 26 MPa, 14 days 34, and 20 days 44. What we have done is we have estimated what is the percentage strength of OPC at 7 days. Okay, at 28 days means 26 by 44 is giving 59%. Again, what is the percentage of strength at 14 days? Okay, with respect to 28 days. Again, our OPC M35 grade concrete got 78% at 14 days and 59% at 7 days. So again, because here we have focused 7 days and 4 days. If you observe, see here almost 7 days, 14 days, the stripping times as per IS 456. Here again we have plotted the graph, between the percentage composite strength of concrete again the various types of the concrete with various types of cements. Here our OPC got 59% at 7 days. So here we have taken this 59% as the baseline, and we have observed at what duration the 59% of strength is getting by other cements like PPC, PSC, and CC. Okay, if you see our composite cement is getting nearly 9 days out of 7. Again, again PPC 8 days. Okay, so and again at 14 days also. Here we have our OPC is getting 78% of its 28 days at 14 days. Therefore, again we have taken this 14 days at 78% is the base. Again we have compared at what ages, at what duration our other remaining cements are getting the same percentage, 78%. If you observe, so this is our other cements getting at the same strength at 16 days, 17 days likewise. So again, we have tabulated the same. Here, the stripping time for OPC is 7 days. And if you see the Portland, our PSC, slag cement and Portland cement, glass based, the same stripping time we are getting for PSC is at 8 days and PPC is at 9 days, again at the composite cement at 9 days. Okay, again is 7 days of OPC. Similarly, our at 14 days stripping time, so our OPC is 14 days, and the other cements are giving the strength at 16 days and 17 days. So therefore, the conclusions we have drawn from our study is the 7 days and 14 days strengths obtained in concretes made with OPC could be obtained only after 9 days and 7 days. Okay, our stripping time for concrete made with OPC is 7 days, but wherein if you use the other cements, other blended cements like PSC, PPC, and CC, so this time is delayed for another 2 days, 9 days. Again, at 14 days, again this is time delayed by 3 days, 17 days. So therefore, the stripping time of blended concretes is delayed by 2 days for 7 days and by 3 days for 14 days. So these are the observations we have made from our study, arriving the stripping time for concretes made with blended cements. So coming to my topic 2, so this is also one of the sustainable development using the alternate coarse aggregate, because nowadays our natural resources, our fines and coarse aggregates are depleting soon because of the high-rise constructions, and so therefore we need to save our natural resources by using the alternate sustainable materials. Okay, so this is one of the new aggregate we have developed. And we have MOU with NTPC and also with our national organizations called Ecocarbon Private Limited, and also we had MOU with these two organizations to make some structural engineering studies for concretes made with nano concrete aggregate. So this nano concrete aggregate is the new material. This is the one of the industrial byproducts. Okay, and this is produced from from 76% of the fly ash. This nano concrete aggregate. So this is 76% of fly ash with 20% of cement along with mineral admixtures. So this aggregate is made with almost 76% of fly ash. Okay, nowadays we are using this fly ash as a cement substitute. Okay, up to 25-30% we are replacing it as a cement. But here these aggregates made with the complete fly ash material. Okay, the total compost is 76% of fly ash with 20% cement and another 4% mineral admixtures. Okay, if you see this diagram, this the left side is a natural stone aggregate, and here the middle one is it's a concrete made with NACA, and NAC, nano concrete. Nano concrete means the concrete made by fly ash and cement and some mineral admixtures. Okay, So they will prepare the concrete bunds, okay, like our stone bunds. What we are doing to get the natural aggregate, our natural stone aggregate, we are taking the stones from hillocks and we are crushing it using our crushers, okay. And that metal that material we are using as a coarse aggregate. Similarly, this new material called nano concrete aggregate made with stone-like nano concrete bunds, okay, and these will be crushed by our crushers, and these material will be prepared, these aggregates. So this is since 76 to 80% of NACA being as fly ash. So this is one of the promising products for promoting mass scale utilization of fly ash with potential to consume total fly ash generation. So this is the new material made with complete fly ash and 20% cement and 4% mineral admixtures. So if you see some of the specifications of this nano concrete aggregate, so this product is cast as stone and then broken in jaw crushers. Broken multiple phases of aggregate are ideal for better bonding. So the specific gravity of this nano concrete 1.9 and the water absorption is 1%. Here, this nano concrete made with some 50 to 80 MPa strength, and these concrete bunds will be crushed in crusher and made this coarse aggregate. Okay, so here low cost product trending high strength and ideal for structural concrete of grades at 40 to 70 MPa. So the genesis for developing this material, this sustainable aggregate made with fly ash. So this is the situation where the Bangladesh. So in order to meet the need for the aggregate of in the absence of hillocks, they break clay bricks in jaw crushers. Okay, so up to for low strengths of concrete they are using. But whereas to meet high strength concrete, again Bangladesh importing the stone from India. So similar conditions prevail in North India, necessitating to produce natural stone for further places, because some of the even if you take Sri Lanka, they are also stopping this mining process. They are also importing the aggregates from neighboring countries. Similarly, some of our northern countries also, they are also planning to stop the mining, and they want to procure the stone aggregates from neighboring states. So therefore, keeping this, they have developed, inventors developed this fly ash aggregate. So this is the process of making fly ash aggregate. So this is the mixture of fly ash and cement plus gypsum plus another mineral admixtures. If you see the proportion of this concrete, so this is fly ash 1400 kg per meter cube. OPC, so this is 76%, 20%, and gypsum, and this is the proportion 1:5:20, and similar the equivalent proportions for our conventional concrete. This for comparison purpose, we made some mixed proportions. So this is the way this concrete made with roller mixers instead of our drum mixers. They are, and this is the type of concrete we get, and we store it in containers, and they will cure it, and they will take the bunds, and those bunds will be crushed in the crushers to make aggregate, fly ash aggregate. So this is the fly ash aggregate. This is the 20 mm size. Middle one is 20 mm size coarse aggregate, and this is 10 mm size coarse aggregate. And this is the this concrete is completely, it's a completely made with fly ash, cement, and gypsum. Okay, this is one of the sustainable development. And of course, this is the some comparisons made with our nano concrete with our conventional concrete. This is the way we have to prepare the specimens, and these specimens will be crushed in the crusher. And this is one dome structure is completely made with nano concrete, because initially we observed if you use that nano concrete for structural engineering purpose, we have got some issues because that is not possessing that much flexural strength. So therefore, if you make it these structures, domes or arch type structures, because that concrete is very strong in compression of that nano concrete, because for some up to 80 MPa, MAT, M50 to MAT we are getting. So therefore, the dome types of structures that concrete is very suitable. Again, if you see the your RCPT, we have conducted the this permeability test also. If you observe this nano concrete is 405 against our conventional concrete, which is 4346 coulombs at 98 days. So we have taken our fly ash aggregate, and for structural engineering studies, we have taken 3 specimens, 3 RC beams. The first beam is we have taken 100% natural aggregate plus 0% nano concrete. This NACA means nano concrete aggregate. The aggregate made from nano concrete. Your nano concrete is made with complete 76% of fly ash, 20% cement, and 4% the other mineral admixtures with gypsum. So this is we have taken the conventional beam, which is 100% natural aggregate. In the second specimen, we have taken 75% of natural aggregate and 25% nano concrete aggregate. Similarly, the third specimen, 50% natural aggregate and 50% our nano concrete aggregate, means 0% NACA here, we are 25% and 50% replacements. So we have conducted the test for our natural aggregate as well as nano concrete aggregate. This is the nano concrete aggregate, and the specific gravity is 2.1, fineness modulus is 7.4. If you observe this impact value, this is very. I told you, okay, we can make up to MET also with this proportion. So therefore, here the impact value also we have observed. Okay, high 54.9 as against our 30% in our natural aggregate. So therefore, easily we can use this material for as a roadworks also, for aggregate for roadworks also, because it's possessing high impact value. And these are the experimental studies. Here we made 3 beams which are designated as RCB1, RCB2, and RCB3. This is the geometry of our specimen. We made for all 3 specimens, we have made all the geometrical properties are same, because the only variable is the percentage displacement of our nano concrete aggregate, or simply we can call it as fly ash aggregate, because the majority of the component or constraint is fly ash for making that concrete bond. So therefore, here this is the geometrical configuration of our beam RCB1, RCB2, RCB3. The cross-section dimensions to 100 by 250, and the longitudinal steel at top compression is 212 mm and tension is 312 mm. Again, the shear steps are the same, 8 mm diet, 2 leg steps at 150 mm center to center, and the overall span is 8 mm. Because initially, because of some shortage of fly ash aggregate, now we have procured ample amount. Here now, this is with scarcity of or shortage of aggregate. Initially, we have planned small beams. These are the specifications, and here width of each beam is 100 mm, depth is 200, effective span, and also the longitudinal steel reinforcement, top 212, bottom 312. Shear steps are the same for 3 beams, and water cement ratio 0.45. And these are the cube compressive strengths, split tensile strength, and yield strengths. So here these are the compressive strength of concrete, partial replacement of NACA, nano concrete aggregate. For conventional concrete, 0% replacement means 100% natural aggregate. So these are the compressive strengths of our M35 grade concrete. M25 grade, this is 23.33. This is M25 grade concrete. We have for experimental investigation, we planned M25 grade concrete. So this is 23.33 and 34.83, 28 days, and 25 for 25% replacement. If you observe the composite strength at 7 days, again it's 27.33 as against our natural aggregate 23.33, and at 28 days we got 36.5. Again for 50% replacement, so this is 21.5. Again here you can observe at 50% replacement, slightly our composite strength is getting decreased. 28 days 32 MPa. Similarly, these are the split tensile strengths of three concretes.
Dairy. Okay. We'll write here.
Here,
One dairy is enough. Only 1 second, sir.
yes, sir. Sir, shall I continue? Hello, madam?
Continue, sir.
This table shows the properties of reinforcement used in three beams, RCB1, RCB2, RCB3. Here we have used two types of reinforcement. One is longitudinal steel at compression tension, both are 12 mm diameters, and stirrups or shear reinforcement is 8 mm diameter. Therefore, we have tested this the properties for both the diameters 8 mm, 12 mm. So these are the yield stress we have got 540 MPa and 550 MPa. Again, the percentage elongation 17.5. The reason for conducting these tests is because in design, whatever the suppose if you assume it's FE 415, FE 500, but these days, okay, all high yield strengths of steel is available or available in the market because FE 400, FE 550D, FE 400D. So therefore, in design, we have considered that this 540 only, whatever the yield stress we have got during our experimental test, the same yield strength used in our calculation purpose or in our design purpose, in design. So this is the experimental setup of reinforced concrete beam. We have tested all the three beams in our universal testing machine with 40 tons capacity because the span is less. So this is the experimental setup, and this is the mode of failures. This is RCP1 before failure, and RCP2 during loading, under loading, and RCP1 before failure and underloading and after failure. If you observe, this RCP1 is it's 100% natural aggregate and 0% fly ash aggregate, or we can call it as nano concrete aggregate. Okay, so this is the mode of failure. Here you can observe the mode of failure is it's a flexure, and these numbers indicates the load stages. And similarly, RCB2, so before failure, this is underloading, and this is after failure. Again, the mode of failure is it's a flexure. Hello. What about the presentation, madam? Is it visible? Madam, is my presentation visible? Hello, madam.
Yes, sir, it is visible, sir. Once stop sharing and again start sharing.
Hello. Hello, madam. Am I visible now? Audible? Hello?
Sir, can you rejoin the meeting, sir?
Madam, am I audible?
Yes, sir.
Yeah, sorry for the inconvenience. Here some net fluctuations are there, and I will proceed with the same slide. So these are the two types of reinforcement we have used for our investigation, and we have tested the mechanical properties of both the steels. So already I have explained about the failure conditions or mode of failures for the three beams. Here you can observe the beam 1, RCP 1 failed in flexure, RCP 2 failed in flexure, RCP 3 at 50% we have observed slightly the mode of failure change from bending to shear in RCP 3. Here RCP 3 is it's 50% our natural aggregate and the 50% is our flash aggregate, which is called nano concrete aggregate. So here these are the experimental results or the principal test results. Here if you see this, our RCB1 with 100% natural aggregate failed at 120 kilonewtons. This is 100% natural aggregate and 0% flash aggregate or nano concrete aggregate, which failed at 120 kilonewtons, whereas RCP2, which is 25% with our natural aggregate and 25% our flash aggregate and 75% natural aggregate failed at 140 kilonewtons, and RCP3 is 50% and 50% flash aggregate. The our load carrying capacity. Here, if you observe this at service load, here if you observe the deflections and crack widths, so our RCB1 with 100% natural aggregate, the deflection observed is 5 mm, RCP2 is 4 mm and 3 is 5 mm. If you see the crack widths, service load again, crack widths at here 5% replacement or less than depending on other. So here from the observations of 3 beams, we can conclude or we can suggest the RCB2 made with 25% flash aggregate, which is called as nano concrete aggregate, and 70% natural aggregate failed at 15% higher load than the beam RCB1 made with 100% conventional aggregate. Here RCB2 with natural aggregate flash aggregate is exhibited with values at companion beam. Similarly, made with 50 our aggregate, which is flash aggregate, and 50% natural aggregate failed at 17% lesser load than the RCP1 made with conventional aggregate. Here the mode of failures observed in RCP1 and RCP2 are flexure, and RCP3 slightly the mode of failure changes from flexure to shear. So therefore, based on the current we can suggest up to 25% replacement. Again, we are further expanding these experimental studies by taking the natural beams with 3 meters length. Because of shortage of aggregate, we could able to common beams. We have got aggregate from NTPC, and we are continuing further test with the same material. So this is about my second topic, use of fly ash aggregate, which is also called as it's a nano concrete aggregate. Nano concrete aggregate means the aggregate made with no coarse aggregates. It's a 76% and 20% and other 4%. So these are the observations we have made during our investigation. What I have chosen in this current lecture is it's a suitability of recycled coarse aggregate. Again, we have used recycled coarse aggregate in shear critical reinforced concrete beams. This is one of the MTech dissertation work done by my MTech student. These are the this is the they are prepared process. We have labor and we are a process making of recycled aggregate from the demolished concrete. This is the refining of collected recycled material, and here we have planned 6 here natural aggregate beam, 0% recycle and 100% natural our aggregate. This is we have provided any shear reinforcement. Again, NAB2, again 0% recycled aggregate and 100% natural coarse aggregate. Okay, but here we have provided shear reinforcement. We have designed this beam for shear reinforcement, but the first beam we have not designed purposefully or deliberately. We have not designed, we have not provided any shear reinforcement to ensure, to make sure that the mode of failure we are getting is observed is shear. So similarly, we have to recycled aggregate and natural coarse. Similarly, RCA, we have used 50 recycled aggregate and 50% natural coarse aggregate. RCAB3, 75% recycled coarse aggregate and 25%. Again, RCAB6, we have used 100% recycled coarse aggregate and 0% natural coarse aggregate. These are the 6 beams we have planned for our experimental investigation, and this is about the here a specimen is 1 and depth is 2, span is 1500 meters. The about span is 13. The geometrical properties for all the specimens are same. Variable is the percentage replacement of aggregate. So here 50 is width, 250 mm is depth, and the effective span is 1.3 meters to depth ratio. The flexural reinforcement at bottom is 316 and top is 210 and the water cement ratio is 0.5, and these are the cube compressive strengths we have achieved at 28 days. This is for the different concrete specimens, because the slight variation, because these beams were cast at different durations or different and also this and this is the shear reinforcement. Also 5 beams, and deliberately we have not provided any shear reinforcement to the first beam. Okay, without shear reinforcement. This is about properties test specimens. Here this is the in the graphical form. This is the longitudinal section with overall span 1.5 meters. Our cross section dimensions are 100 by 50, and again we have the mechanical the reinforcement in our experimental investigation, because it's our regular practice to test all the material, whatever the materials we are going to use for experiment. We need to test it, and we have to use the actual values. Okay, not assume. Simply if you assume 415, 400, okay, that is it's not considered. Therefore, whatever the stresses we are getting with our experimental observations, these stresses will be used in our design. So this is our coarse aggregate. If you natural coarse aggregate, so this is our normal natural coarse aggregate, and this is the recycled coarse. So this is the refined from the concrete. The processing is done. We have this coarse aggregate gravity. Specific gravity of recycled coarse aggregate is 2.63. Natural is 2.7. Again, water absorption. If you recycled aggregate slightly high, this because of waste material with the store for the water absorption for recycled coarse aggregate, and the natural coarse aggregate is 0.7, and the impact value slightly this is less compared to the natural coarse aggregate. Portion we have used for making the 6 RC beams. We have used M25 grade concrete to 2.43 with water cement ratio of 0.5. This is the mixed proportion or mix for all 6 beams. So this is the form same. Our 100% natural coarse aggregate, and second beam is also 100% natural coarse aggregate, and third beam 24% recycled, 20% recycled 70% natural coarse aggregate. Similarly, the fourth one 50%, 50%. Again, 75% natural coarse aggregate and 25% recycled. And sixth one is 100% recycled coarse aggregate. And this is the construction of molds for all the molds. Okay, with brick walls and smoothly finished for before casting. We are not using any. Okay, we are casting the specimens. Okay, in these molds. Okay, these molds also prepared with bricks and well finished. This is the casting of specimens with this was our MTech students also helping, or UG students also helping with helping to him. So this is the casting of beam specimens and other the control specimens, so cylinders and cubes. This is the curing of for 28 days, and after 28 days we have removed, demolded the space. These specimens were test for ready for testing, and the NAB one. This beam was 100% natural coarse aggregate, 0% recycled, and this beam was not provided any shear reinforcement. Deliberately, we have done this because to make sure that beam and shear. So what this is the observation after testing. So this beam, whatever mode of failure, it was satisfied. This is the beam was failed in shear mode of failure. Again, NAB2, this is 100% natural aggregate and 0%. Again, yeah, so here in the topic said observing the performance of recycled coarse aggregate in shear critical, because here we made the shear is critical because we have allowed, though the beams are provided and designed for, but we have assessed what is the shear carrying capacity of because we made all the beams to fail in shear. We have designed such a way that though the shear reinforcement is provided, without the mode of failure, because we need to shear carrying capacity, how the recycled coarse aggregate performing with critical beams. NAB2, and this is the NAB2 after testing. So we have allowed this beam to fail in shear. It was failed in shear. Similarly, RCAB, okay, this is 25% recycled coarse aggregate and 70% natural coarse aggregate. This is before testing. You can see some failed in shear. And this is RC4, so 50% natural coarse aggregate, 50% recycled coarse aggregate. Again, the mode of failure you can observe. This is again failure is shear. RCAB5, 70% recycled coarse, 20% natural coarse aggregate. Again, a mode of failure is shear. And we made all the experimental loading frame available in our. We have loading frame where we need to set up our beams before testing, and this is the arrangement for measuring the deflection. We have arranged the dial gauge bottom of the. We have applied a 2-point load for testing, and this is the hydraulic jack. Okay, we have it's a programming loading control unit to apply the load, and this hydraulic jack, okay, will push the beam and okay for like deflections and crack widths. Therefore, the comparisons were done at the same load shear force. Okay, because this the 53.33 kilonewton is the service shear force for NAB2. Remaining beams also compared at the same 0.33 kilonewtons. We compare because beams were failed. Madam,
So your screen is not visible. Sir. Yes, sir, it is visible now.
audible.
Yes, sir. Sir, your voice is not audible, sir.
John.
Sir, your voice is not audible, sir. Sir, your voice is not audible, sir.
Yeah, sir. Sorry for
Yeah.
the inconvenience.
Sorry.
The internet issue. I don't know. Suddenly it has encountered. Morning also I've tested, but it's working well. Sorry for the inconvenience. So actually we are end of our presentation. These are the principal test results we have derived from our experimental observations with recycled coarse aggregate. Here, as I already told you, our companion specimen is NAB2, which is 100% natural coarse aggregate with 0% recycled aggregate. We have taken that service working load as the reference for all the beams because we have to compare the deflections and crack widths for at the same load. So therefore, if you observe the deflections and crack widths at the service load, so here the beam natural aggregate 2.54, deflection 0.1. Similarly, NAB3 70% recycled coarse aggregate and 25% which induce 3.2 mm and 0.25. And RCAB2 3.3 and 0.3. RCAB5 with 70% recycled coarse aggregate and 25% natural coarse aggregate, and RCAB6. Okay, so among all these beams, what we observed is if you see the RCAB4, which is 50% natural coarse aggregate and 50% recycled coarse aggregate, induced 0.3 mm crack width at service load. And if you see look at the other two beams, RCAB5 and RCAB6, the induced 0%, which is beyond our permissible with the crack width for our RC members under cracked sections. So therefore, and similarly, our crack width 0.3 and deflections also, if you observe, if it is beyond 50% replacement, again our deflection values are slightly increased. So therefore, with our experimental observations, so these are the load carrying capacities of different beams, all 6 beams. So moment crack width curves. So these are the conclusions we have drawn from our 6 beams. In the present context of fast depletion of concrete making materials, the need of an alternative source for cement, sand, coarse aggregate is urgent. As an alternative to natural coarse aggregate, recycled coarse aggregate, having its origin in Europe during the World War II, is most suitable and rewarding, notwithstanding initial setbacks in the preparation of RCA, because we need the mechanism, processing mechanism must be initially bit cost, but whatever the expenses we are incurring, that will be offset by our advantages from our structural properties. So in the investigation undertaken, RCA, that is recycled coarse aggregate up to 50% in reinforced concrete shear critical beams is appropriate, because at 50%, if you observe our the crack widths are meeting to permissible crack widths for that is 0.3 mm. Therefore, use of RC up to 50% in reinforced concrete shear critical beams is appropriate. Use of recycled coarse aggregate in shear critical RC beams results in small percentage reduction in shear strength. At service load, the decrease in deformations, deflection, crack width increased with increasing the percentage of RCA. Okay, if you observe, if you the percentage of replacement is more, our deflection values and crack widths also slightly getting increased. Therefore, we can limit our recycled coarse aggregate up to 50% from our observations. Adoption of recycled coarse aggregate up to 50% of total coarse aggregate appears reasonable on the basis of current study. The use of higher percentage of recycled coarse aggregate becomes possible in the country as the refining mechanism of RCA reaches its peak. Okay, if you make sure that our refining mechanism in large scale and well processed, we can use more percentages also. Okay, but based on our observations, we can suggest up to 50% of the replacement of recycled coarse aggregate with our natural coarse aggregate is reasonable based on our current study. So these are the differences we have taken. Thank you very much once again for giving me this opportunity. And okay, once again, please regret for small technical issue or regarding internet encountered. This is the end of my present talk. Yes, sir. My presentation is over, sir, from my side.
Hello everyone. If you have any doubts, you can feel free to ask.
If you have any queries, okay, please you can post it in our chat box or
Sir, someone asked, what will be the cost impact, sir?
yes. Initially, as I already told you, the refining process, okay, making the separation of our coarse aggregate from our concrete, okay, it may take some okay, time consuming also. Some initial cost we need to incur, okay, for the engaging the labor and all. But slightly the cost of the recycled coarse aggregate, okay, that including the processing and all, the initial cost is more. But at the same time, if you observe, we are saving 50% of natural aggregate. Okay, up to 50%. If you, I think you might have observed my experimental observations at 50%, we can replace. Okay, therefore, whatever the initial cost we are incurring, so that will be offset by our okay results, our positive results, or the results, whatever the benefits we are getting from the experimental observations, automatically that will be offset by the initial cost. But slightly for that's why if we make sure that of our refining mechanism is okay a bit high, certainly the concrete made with recycled coarse aggregate will be certainly cheaper, because we are saving 50% natural coarse aggregate. Not only saving, and also we are saving a lot of natural resources, okay, for sustainability point of view.
Are there any
Similarly,
questions?
I have okay, discussed the second topic. Okay, I have tried two types of sustainable aggregates. One is the aggregate made with fly ash, because okay, till now we are using the replacement for cement only. Okay, so now we have used up to 50%. Again, we are expanding our studies up to 70%, because in our observations, we need we have found some gaps, because that water absorption, percent of water absorption also we need to test it, and we have to make the corrections. But definitely the concrete made with fly ash also can be used up to 50%, 70% also.
So there is another question, sir.
Yes.
Is it feasible to use recycled fine aggregates?
Recycled fine aggregates, because the problem is okay, that adhesive material, okay, that aggregate we can, the mainly the bond between aggregate and our the purpose of here, see, we are using up to 250 the compressive strength of our coarse aggregate. That granite stone is up to 250 MPa, but still, even though that is 250 MPa, we are making the concretes the average strength of 20 to 30 MPa, because that the strength of that natural coarse aggregate almost redundant here, because that's such a high compressive strength material we are using, but we are making the concrete up to 20 to 30 MPa. So here the main this one is the transition zone, because why the even though you are using 250 MPa aggregate, but why you are getting 30 MPa, 40 MPa strength? Because that the transition, because the bond between your coarse aggregate and the other material will be ensured by your mortar or cement. That is the that is why we are getting such low strength 30 MPa, 40 MPa, even if you use high strength concretes. Okay, so mainly for fly ash, for recycled fine aggregate, because the processing is very tedious. Okay, we can use the coarse aggregate, but don't think so we can use it for fine aggregate. But here you can use our bottom ash as a replacement of your fine aggregate. Bottom fly ash, whatever the bottom ash you are getting in our national thermal power stations, that can be replaced with fine aggregate. But I don't think so. The recycled fine aggregate, but we have not made any test on recycled fine aggregate. Any other doubts, madam?
So someone asked, can we use this technique like in industries, bridges, and etc.?
Yes, madam, definitely, because a technique means the our fly ash aggregate. Definitely, certainly we can use it, because the strength of your fine aggregate is in the order of 50 to 80 MPa. Whatever the concrete we are, whatever the aggregate we are making, we are making the stone bunds, our concrete bunds. The strength of that concrete bund is 50 to 80 MPa. Okay, we are making 80 MPa strength concrete with finer material, very finer materials like fly ash, cement, and gypsum. Okay, we are not using any cement, our sand and coarse aggregate. Definitely, we can use this. We can extend this coarse aggregate for other applications also, like bridges and other structures, because the strength of that, the compressive strength of your the aggregates made with fly ash, which is also NACA, is high, up to 80 MPa is there. So certainly we can use this NACA aggregate for other applications also. Already in NTPC, they have constructed a two-storied building with 100% replacement of coarse aggregate. That's why we need to extend the studies up to 100%. Okay, because of shortage of material, we could use it up to 50%, but our further investigations we are using 100% also. Hello, madam. Any other questions?
Sir, someone is asking for to tell the references where we have used it in India.
Yeah, in India, I will share one. If you share your mail ID, definitely I will share the information. As I already told you, we have constructed two-storied office building for NTPC using 100% glass aggregate. We have not used any natural coarse aggregate. The your entire coarse aggregate replaced with our fly ash aggregate only. Now that already 5 years, for 4 5 years back, we have constructed. Still, it is functioning well without any. We have not observed any cracks so far. Okay, it's functioning very well. I will share that paper. We have published one paper also in one of the conference. Two-storied building, office building we have constructed.
Okay, sir. If there are no more questions, sir, we'll wind up the session.
Thank you, madam. Once again, I thank the organizers for giving me this opportunity to share the experimental observations which were derived from our very dedicated MTech students. These are the 3 MTech dissertation works I have summarized and prepared the presentation. And once again, I thank all the participants for the patient listening. And please regret for that technically, actually, I have not expected this internet issues.
It's and kindly share your PPT, sir.
Yeah,
We
definitely.
are
Madam.
asking.
Yes, yes, definitely. I will share the PPT.
Thank you for this wonderful session, sir. Apart from all those issues, we have understood the topic very clearly, sir.
Okay, ma'am. Thank you, madam. Can I leave, madam?
Yes, sir, you can leave, sir.
Yes, yes. Thank you once again, all the my colleague participants from industry as well as from academy. Once again, I thank the organizers for giving me this opportunity. Thank you.
Thank you, sir. I request all the participants to fill the feedback from given in chat box. Really, in chat.